Hi, good afternoon to all our dear attendees. I am Pankaj from Midas IT. I look forward to business development, technical support, and sales for international market, for basically for Africa and Middle East on behalf of Midas IT. I welcome you all to this webinar session, which is in which we would be covering an case study for Manyovu Bridge, which is a long span RC girder bridge, which would be delivered by our user expert engineer Brian Alituha, who is working as a senior bridge engineer with Kaburu Okelo Consulting Engineers in Uganda. Initially, I would just give a brief about Midas company overview, the user companies of Midas software across the globe, and then we would invite our expert to take a lead forward on case study web bridge, which is Manyovu bridge this time. Without wasting much of the time, I would just give you an introduction on what type of bridges Midas-Civil can handle. So Midas-Civil is an all-in-one tool which can design all type of bridges, starting from the conventional bridges, which covers culverts, frame bridges, slab bridges. It can also cover precast, integral bridges, steel girder bridges, or steel box girder bridges. And for the complex type of bridges, it has capabilities to deal with box girder bridges for different types of construction methods like balance cantilever, incremental launching methods, moving scaffolding method, segmental method, and full staging methods. So the best part about Midas is we have dedicated wizard options in the software for each type of bridge. So for all the type of bridges, you have a template wizard in the software wherein you can just input the geometry of the bridge, and then we are good to go with the modeling further. It also has capabilities of designing more complex type of bridges like cable stay bridge, extra doors type of bridges, and suspension type of bridge. Also, for Midas-Civil, it has a design feature as per all standard codes. So we cover British standards, Euro standards, American standards, and all international standard codes like Japanese, Chinese, uh, or for other regions particularly. So we can do the design of all these type of bridges with desired specific code as per the region. I would just give a brief about Midas company. So Midas as a whole has #1 market share in civil engineering software segment, and we have over more than 450 engineers and professionals working under Midas to serve to the consulting companies and engineers across globe. We have more than 120 distribution centers and more than 10,000 number of companies who are using Midas softwares for flagship projects. We have so far sold more than 60,000 number of licenses across worldwide. Uh, to give brief about our network, we have our headquarters in South Korea and our branch offices in US, Japan, China, India, from where we deal for Africa and Middle East market. We have UK and UAE office where we look for other regions. And we have channel partners across globe. So we have more than 90 countries where we have channel partners for Midas supplier and support. To introduce you well with what Midas does, we provide services on engineering consultancy for bridges, for buildings, for geotechnical analysis, and for mechanical analysis. And in parallel, we also provide these software solutions for these type of consulting services, like for bridges, buildings, geotechnical, and again for mechanical engineering. So as we have our involvement both in doing the consultancy service as well as the software providers, we provide that optimal solution for practical engineering with the synergy we have developed for practical engineering. To introduce you with Midas family products, we have segment line for buildings and structural engineering, where we have softwares called Midas Engine, which is a 3D modeling analysis and design tool for building structures. We have Midas Design Plus, which is an elemental design tool, and Midas D-Shop, which can generate the drawings and the drafting part for Midas. Under bridges, we have Midas-Civil, which is an all-in-one tool for bridge design, and Midas FEA, which is required for detailed finite element analysis for particular element of bridge. For geotechnical, we have our 3D software solution, Midas GTS, and for 2D, we have Midas SoilWorks. Under mechanical segment, we have Midas NFX and Midas FX Plus as our software products. We feel pride to have most of the MNC companies on board, and also the renowned local regional companies who are involved into consulting engineering services for Africa and Middle East region. I've listed a few of them, which covers AECOM, Arcadis, Atkins, and Renarded, Sistra, who are the market pioneers and are our power users currently. So we take pride in having them on board. Apart from this, we have many other companies who are our power users, and we also feel pride to have them on board too. So without taking much of your time, I would like to invite Engineer Brian, who would be our expert for today's session, so that we can move ahead with today's agenda.
Good afternoon, everyone, or good evening, depending on where you are. Today, I'm going to be the one presenting. Let me just set my presentation. The contents of this presentation are going to be, I'm going to have a personal introduction, a project overview, why I used Midas-Civil, and the design of this bridge, the Manyovu bridge, a demonstration of how you use Midas in order to get the actions and the reactions on the structure, and the different results that we're able to obtain, and of course, a conclusion. To start with, I'm Engineer Brian Alituha. I'm a senior bridge engineer here at Kaburo Kelo Consulting Engineers. Who is Kaburo Kelo Consulting Engineers? Kaburo Kelo Consulting Engineers was founded in 1984, and we've worked on various projects in and around Uganda, and in different countries that includes Uganda, Kenya, Rwanda, Tanzania, Burundi, South Sudan, and Somaliland. We've worked on bridges, culverts, we've done education centers, research centers, industrial buildings, warehouses, and some of which even had cold storage facilities. We've worked on multi-story complexes in reinforced concrete. We've also worked on large span structures, especially the ones that have big spans, 40 meters, 45, 50 meters. We've worked on earth retaining structures, water retaining structures, elevated water tanks, silos, domed structures, marine structures. Just to give you a brief of some of the projects we've worked on, these are some of the projects we've worked on. The one on your right is called Inzovu. The one on the left, sorry, top left, is called Inzovu. It's a structure. There are structures that are actually sitting on 8 acres It includes a hotel and an office building with a combined basement. Then the one at the bottom, it's a water treatment plant that was constructed here in Uganda. It's one of the largest water treatment plants in East Africa, if not in Africa. And it includes water tanks that are as huge as 50-meter diameter and 15-meter height. When the one in the middle is a URA building that is found here in Uganda. It's a Uganda Revenue Authority building, and it's a 22-story building. The one in the middle at the bottom is Zigama CSS that is found in Rwanda. Then the one on the right, which is quite similar to the type of structures that we are going to discuss today, is a bridge that is crossing the River Nile, and it's called Para Bridge. It's a pre-stressed bridge, post-tensioned, and it's a 40-meter span bridge formed of 15 spans. The one at the bottom, we've worked on different bridges that are composite in nature, that is steel and concrete, a concrete deck. And we've worked on different spans, 30-meter, 35, 25, 15-meter spans. Let me dive into the presentation. Why did I have to use Midas-Civil? If you've been using finite element analysis in your design, I'm sure you can agree with me that this is one of the methods that takes a lot of time, especially if you're going to use hand calculations, because then you have to go through all the modalities of coming up with your analysis. You have to get the shape function, derive the element equation, get the stiffness equation, and given such a bridge that we have, then you have large matrices, then you have to use Gauss elimination method, if it's the one that you've chosen, in order to get the primary unknowns, and then you start interpolating the results to get maybe a tabulated data or a graphical data. By the time you do all that, you will have taken almost a week in just analyzing a very simple element or a very simple structure. Now, Midas comes in handy to actually bring this with ease. You can do all that in Midas in less than a minute. Like the bridge that we are going to look at, it was done in less than 30 seconds. So the work you would have done in a week or 2 weeks, you are condensing it in only 30 seconds. So that's why we had to select the use of Midas-Civil. Then the output of Midas is just on its own level. The graphics, as you will see, if you've not used Midas, is just so good. It's just appealing. And then Midas is a widely used software. If you're communicating with another engineer around the world, you will easily communicate with softwares that both of you are using. So if you're not using a software that is commonly used, then somehow you're in a docket. But if you are using a software that the other person is using, you can easily discuss issues and solve issues with ease. So that's why we had to go into the use of Midas. Project overview. This is the kind of bridge that we're going to discuss today. It's a bridge that was designed in using a finite element analysis. It's a continuous slab bridge, 15-meter span at the centers. In the extreme ends, it has about 21-meter span. The deck width is about 11, and the riding area length is about 8 meters. It has 2 sidewalks, each on either side is 1.5 meter. Then a concrete barrier that is 0.4 and 900 millimeters high. The radius is 30. Deck thickness that was chosen was 800, of course, increasing to 950 at the supports. We put a crossfall of about 7% in the carriageway. As you might see in this photo, it's a curved slab bridge, multiple curves, skewed supports. You can look at the skewed support at the abutments. Then the abutments are winged. They are usually not common. So And then it has unsupported long spans in the center, as we said, 15, on the outskirts 21, and a super elevation that was put of 7% to counteract centrifugal forces, then 5 bearings, and of course a cantilever on either side of 1.5 meters. So such a bridge would really be hard to calculate manually. You take ages, months, if not a year, just calculating or doing even just analysis. Or if you are to use, let's say, Excel sheets to just come up with a finite element analysis, it will still take you quite some time to just understand even the results of each element. So this is when Midas comes handy. Why did we choose to use a slab bridge? First of all, just as you've seen, the slab bridges accommodate a high skew, like the one that we have in our bridge. It's a very high skew, so to accommodate it, you are either going to use a slab bridge or sometimes a box girder bridge. But of course, then that comes with its own disadvantages. The cost, the expertise, the fields, they increase. Then here in a slab bridge, you use conventional concrete, which is normally cheap. It has very good aesthetics because you have a flat soffit. The formwork is simpler and less costly. You have smaller thickness of the deck. You can see this is just 800. From afar, it's a very small thickness. It's simpler arrangement of reinforcement. You don't need stirrups. Reinforcement is evenly distributed, so you don't have reinforcement that is that needs expertise to mold, to bend. So the reinforcement is simpler to place. Placing of concrete is also much easier because you have just a thickness of 800 that you have to place your concrete. Chances of honeycombing are way less because you don't have a lot of reinforcement concentrated in regions. Then there is quicker construction time. The disadvantages that this comes with is that there's greater cost of materials, and especially the dead loads. You can just imagine how much dead load is going on to that middle pier. Because of 800, 0.8 times 25, the dead load, that's around 20. The dead load is really enormous. So that's the biggest disadvantage that comes with the slab bridge. So we used the Euro codes in the design of this bridge, and those are the different types of Euro codes I believe most of you should be knowing. Most of the Euro codes, or even have used them. You've used them. The design working life that we chose, of course, we followed what the code specifies. That is 120 years, according to the national annex to Eurocode, the national annex, the UK national annex. And according to table N8.2.1, it shows you that for any monumental buildings, you have to use, or bridges, you have to use 120 years as your design working life. And of course, for the concrete, we chose to use a cylinder strength of 35 for the deck, substructure 30, blinding 12. And as you might see here, the properties of the different concrete strengths are showed, the relationship between cylinder and cube. The mean strength of concrete is provided. This is a table that is extracted from Eurocode 2, part 1, I think table 3.0. And you can see, of course, one of the things that is very important is to get the strain, to keep the strain within, the strain of the concrete within the allowable strain, which is 0.0035. The material properties, of steel were also, we used also the Euro codes. We used grade 500B, and hence we're limiting our total, the maximum force, the total elongation at maximum force was a minimum 5%. I'm going to just show you a demonstration of what was done. How do we import? How would you import a project from AutoCAD to Civil? Most of us use a CAD because this is an everyday engineering tool. But how would you import? Now, in this case, this is what we did. This is our bridge. We drafted it in AutoCAD, and then, of course, these are some of the different elements that we used. So basically, you have to draw your grillage system or your finite element arrangement. You draw each and every element. You should take note that if you use lines, then these will become beam elements. If you use polylines, that's when they will become plate elements. So this, after designing, rather not designing, after drafting this in AutoCAD, we had to import it to Midas. If you go to Midas and you come to import under AutoCAD DXF file, so you can easily import your file as long as it's a DXF file. Just as you see here, you can either import nodes only, or you can import nodes and elements. So like for our bridge, if you've used lines in your drafting, then you have to import only nodes. Otherwise, they will come as beam elements. Or if you've used polylines to create your elements, then you can import node and elements. And henceforth, you'll be able to get plate elements. So that's the simplest way of doing this. You can see you can easily switch from AutoCAD to Midas by just importing the structure, and hence it quickens your work and hence shortening the time that you would be using to model in the software itself. So back to the presentation. So that is what was done when we're moving or when we're importing from AutoCAD to Midas. So the different finite elements were modeled. What I did is to import nodes. I didn't import the elements, so I imported the different nodes, and then I had to draw using plate elements in Midas, and hence these are the different plate elements that I drew. But okay, this takes really some time, especially if you're going to draw each and every plate. You can just imagine how much time can be taken in drawing each and every of these in each and every plate in this structure. So it takes quite some time, but of course it reduces the time if you're going to use Midas compared to when you're going to do it by hand. You're going to calculate by hand. So for the Pier cap, we used beam elements, and Midas was able to help us in designing such an element. Then the boundary conditions, these are some of the boundary conditions that we used. So at the abutments, it was the slab deck would move freely. Then at the middle pier, it was fully fixed in all directions. And the same applies to the last abutment where it was free to move in all directions. Basically, this was because of the pier height, which was almost 9 meters. So bridge loading. Of course, we all know that the bridge has 3 types of loads: vertical, transverse, longitudinal. So for the vertical loads, we have dead loads. For the live loads, we have our vehicles, either HB loads or HL loads or tandem systems according to Eurocode. Then you have impact, let's say collision on the deck or on the piers. Then the transverse, we have wind action, we have the earthquake load, we have the centrifugal forces. For the longitudinal, we have the braking, thermal, and friction. So all these can actually be input in Midas. And these are some of the loads that we input. Of course, as per code, you have to first specify your notional length. And when you go to the traffic loads code, it shows you this table whereby it specifies that the notional length has to be 3 meters, and any other, which is not an integer, will be called a remaining area. So we divided our bridge into notional lengths. We got 2 notional lengths with the remaining area of 2 meters. And of course, we have walkways on either side of the bridge. And all this has been input in Midas. It's not done from out and then imported in Midas, but it has been done in Midas itself. Then, according to Eurocode, you have to use different load models. And load model 1, it specifies, according to Eurocode, that you have to use a certain tandem system that has 4 axles, and each axle is 150 kilonewtons. And of course, this can be adjusted using the national annex of the different countries. We're using the UK national annex, and of course, which has an adjustment factor of 1.0 for the tandem system. And then for the UDL, the national annex shows the different adjustment factors, 0.61, 2.2, which makes us get 5.5 kilonewtons. And this table is directly inserted into Midas. When you go into the traffic system, when you're loading the traffic load, you just input all these values by yourself. So it makes it very easy for you to be able to get the loading. And then load model 3 was also used. We used an SV196. This means that you are using a basic axle load of 16.5 tons with a gross weight of the vehicle that is 196 tons. This was basically used because of the traffic count, and of course this is a border post. So the amount of vehicles that are going to be crossing and the weight that they are going to be taking, we felt like this was the best vehicle to be used for this bridge. Of course, the Eurocode shows that we have to group our load cases, and group 1 load model, and group 1 A has you have to use load model 1 plus 0.6 of the walkway loads. Group 1B, you have to use load model 2. This was not used because this bridge is more than 8 meters. Group 2, of course, load model 1, braking loads, centrifugal, and so on and so forth. Longitudinal and braking acceleration. This was calculated, of course, manually according to the Eurocode, and we got the braking force of 66 kilonewtons and acceleration force of 100 kilonewtons, which was imported, rather put into the software. And you can see here, we see an acceleration force of 100 kilonewton that is on our deck or acting on our deck. Of course, this is a surface force, so in each node would put 100 kilonewtons of a force. Then the wind forces were also calculated, and of course, according to the code, it shows that you have 2 types of wind forces in one direction. So you have one which doesn't have traffic and one that has traffic. The one that doesn't have traffic is during construction. Then the one that has traffic is during the service life of a bridge. We calculated this and we got these values that you see down here in this table, and these we put in the software itself on our bridge deck. And you can see here a 2.70 kilonewton per meter wind force, and also even the longitudinal direction, we're able to input the force manually into the software. Midas also takes care of the time-dependent materials, the creep and shrinkage. They are automatically calculated. You just have to input in your compressive strength of the concrete and your class of the cement class. That is if you're using Eurocode. and it will automatically draw these graphs for creep and also for shrinkage from the start of loading to the end of loading of your bridge. Also, uniformly distributed dead load on the walkways was also used. We used 5.0 kilonewtons per meter squared, and this was also input directly onto our bridge. Collision forces were also included. If you go to the accidental load code, that is Euro code 1991 part 7, clause 4.3.1, it shows the Pier collision and how it should be considered, as you can see from the photo on your right hand at the top. And this was actually input into the software, as you can see on your bottom screen at the right. And then also the deck collision was input, as you can see from clause 4.3.1, and this was directly put into the software as a force acting on our deck. Temperature loading was also considered. We used the maximum and minimum temperature of 18 degrees and 40 degrees respectively. Also, the temperature differences, the linear and non-linear temperature variation was of the cross section was also included. It can be calculated in Midas, and it's easily put in the software. So it doesn't give you a hard time to calculate and to put into each and every element or plate element. It's very easy to input in Midas. Of course, the results, we use the structure analysis software, that is Midas-Civil 2017 version 2.4. And analysis has been carried out based on the global analysis model. Different load combinations were carried out using the mentioned bridge loads, and reactions of these actions were directly produced by the software. So you would put in the action, and of course the software itself would get you the reactions. It's not a hard thing. The analysis doesn't take a lot of time. It takes a very short time, and then you can be able to get your results. And as engineers, we are very, very, we really want results. So if you can be able to get results from a software, well and good, of course, meaningful results. These are some of the results that we got. This is a very unique tool in Midas-Civil, the influence surface method for calculating the moving load analysis. Maybe let me just show you a little bit how this works. If you come here in Midas, and let's say we have a plate force, we have a maximum plate force of, just a minute. Let me just remove the exponential, make it fixed. Okay, so a maximum moment of 1117 on an element 531. So this is the maximum force. Now, if you want to know the vehicle that causes this maximum force, or the vehicles that cause this maximum force, Midas gives you that. If you come to the moving load tracer, you come to plate forces. That is if you are using plate forces, or beam forces if you have been using beam elements. So you come to moving tracer, you come to plate forces, you come to the different, of course, vehicles that you put, or load combinations, or grouping. So if I come to group 1A and I click apply, you can see the vehicle automatically shows. And this is accurately portrayed. Just if we zoom in a little bit, you find that the tandem system is accurately captured. You see in lane 1, in lane 2, you have load model 1, and in load model 1 and the axle loads of 150. And in lane 2, you have load model 1 with an axle load of 100. And actually, when you go to group 5, which includes load model 3 plus load model 1, the software automatically picks it. You can see here, it has done a simulation of a straddling vehicle, and you can see the maximum force on that plate that we chose. Or this is plate 1, sorry. I had to choose plate, I think it was 385. So plate 385, I hope it's this one. Okay, so you can see that it accurately gets exactly what the code shows. Just imagine if you are going to do this manually. It will take you ages just to do the analysis of this vehicle that is moving along the different lanes. It would take you a lot of time. But what Midas does, in just a click, you are able to get results of the moving vehicle. And you can see it's accurately got, the code specifies that if you are to put load model 1 and load model 3 in the same notional lane, you have to put it 5 meters away. And you can see here, it's actually 5 meters away. So the software makes life easier. It makes life very easy for us. Just back to the software, rather to the presentation. Okay, so that's it for the influence surface, rather for the moving load analysis. You can see here different vehicles that were chosen and the impact that they have on the bridge deck. Of course, you can see, just imagine putting this in your report, and the report specifies, or it shows which vehicle is having the highest impact, or which position of the different vehicles is having the highest impact on our bridge. You can imagine if you are designing a bridge that is, let's say, 50-meter long, or 100 or 500 or 1 kilometer long. It means it will take a little bit of time to simulate the vehicles, even if you're using Excel or anything else. But Midas, everything is just a click away. You just click on an element, you run the analysis, and then it will give you the vehicle positions that are causing the maximum moments or whatever on that element. Of course, satisfaction with moving load analysis is of application as compared to older practice. As you've seen, there's an enhancement of project report, because then your project graphical, it's easily understandable. In engineering or company practice of application of loads as per Euro codes, the program follows strictly what the code says. If it says, when you're straddling the vehicles in 2 national lanes, move them maybe 0.5 meters away, the program will go as per the code. It will carry out the analysis as per the code. Displacement contours were also got, of course, using a finite element analysis, and hence displacement are got accurately. As you can see here, the envelope of moving loads plus static loads, we got a 22.15 meter displacement for at serviceability limit state using that load combination. And we got a displacement contour of 22.15. Oh, that is the same load combination. But you can see how graphical Midas is and how easily understandable. You can get to understand what you're doing with ease. So Midas is a very good software that can help you to do numerous things with ease when you're carrying out your bridge design. And the displacement, of course, with the different, this is load combination 10, and it gives us 32.16. This was at ultimate. And of course, you can even get the plate forces. You can see here the moments, and they're accurately got. You can even get the average node moment, or you can get the moments of each particular element, each particular plate element. You can even get the stresses. You can get either stresses of the top or bottom or both. So Midas, in just a click, you can get numerous results. You can get the stresses of course, now in such a bridge, stresses are very, very critical. We even had to increase the compressive strength of the concrete so that we can counteract the stresses, because the stresses are, when we're using we're using a cylinder strength of 30, the stresses were not passing. So we had to increase to 35 so that we are within the allowable limits. You can see that the stresses here are about 9.75 newtons per millimeter squared, which is within the allowable as per code of practice. You can even get the analysis for a beam element like this one for the Pier cap, so you can accurately get the analysis in Midas. The same applies to the Pier. This was a collision analysis of the Pier, so we wanted to understand, okay, when there is a collision, what happens to our Pier, and we could understand the analysis very well just by clicking. It's just, everything is just a click away. Design. Does Midas do design? Yes, of course it does. And its design is very, very beautiful. It's laid out in a very easy way that you can understand. You can easily get the results and give them to a detailer for him to be able to detail. So Midas makes that easy. And of course, if you need even a detailed report as an engineer, you want to check maybe the Z or the X or the force in the stress blocks, sorry, the force in the concrete, the force in the steel, you can easily get all that when you're just using the detailed report. This is one of the reports. This is the graphical report, which is a bit shortened. Of course, to get these reports, you have to first make a domain of your bridge deck, and in a domain, you have to make subdomains using the plate beam design tool in Midas. And then when you make the subdomains, you can be able to specify the areas. You can be able to check for the provided area, or you can be able to design for that area. And the same applies to the detailed design. As you can see here, it's really very detailed, and you can easily get to understand what is happening when you're using Midas. You realize these are some of the results in the design, and you can see the output is really easy to understand. You can see that this is the element that has been selected by the software, and the element has maybe this type of bars. These are the bending moments that have been considered, and of course the utilization ratio, which is very important to you, because you don't want a utilization ratio that is very low or over and above what is acceptable. Plate column design. Of course, the other one was plate beam design, but you can even do a plate column design when you're using Midas. You do the same thing. You make a domain, then you make a subdomain. The subdomain, you specify the area of rebars required. Then after that, of course, you go into the actual design of your plate element. And these are some of the results that Midas gives. Of course, these are the results that we input, rather we got. And you can see here the walkway design. You can see the Pier design, which is a plate column design. You can see the RC beam, which is the Pier cap design. And of course, the Pier cap, even when it comes to tapered sections, you can even design them in Midas using the section for design. You can accurately design a tapered RC beam. These are some of the drawings that we got, or we drew. We use bundled bars. If you've seen in the design, we realized that using just a single bar would not work. Otherwise, the stresses were very, very high, and especially in the area that is spanning 21 meters. So we had to opt for using bundled bars and increasing the strength of the concrete. So Midas has been very useful, very, very useful, especially when it came to the analysis of the elements using finite element analysis. We didn't take a lot of time. It took a very short time to do the analysis. So Midas came in handy. And then the graphics for the output for the results, as you've seen, it's very easy to understand your results when you're using Midas. You can see the deformation shape of anything, either stress or a deformation or a moment. You can easily see the deformation in a member. So how did I account for the general slab bridge failures? Of course, as I mentioned before, I changed the material properties. I used a concrete of a higher grade, moved from C30 cylinder strength to C35 cylinder strength. And then also, instead of using a single bar, we used bundled bars, which is acceptable as per code. If you check in Euro Code 2, Part 1. Yeah, Midas is really a very unique software. It's one software that I would encourage each one of you to get and to start using. It can do numerous things, especially when it comes to modeling. It's a very rich software and very easy software to use. When it comes to a specialized high-end analysis, let's say you are doing a cable stayed bridge or a suspension bridge, Midas comes in handy. If you are performing a seismic analysis, Midas is a very good software. You will see all the sways, you see everything. Midas gives you a platform that makes you or improves you as an engineer. Thank you.